My name's Steve Willoughby with Bentley Systems, and we're here today to talk about flange plate optimization. And so a few things that we'll cover here is the new automated girder plate generation that's in the latest version of Leap Bridge Steel. There was a new version that came out just over a month ago now. And in there, we also added flange design optimization. And we're also shooting to have another release late this fall, probably November, December timeframe, and we'll have web optimization in there. So we'll hit on that a little bit right at the very end. Now, as far as the automatic girder plate generation goes, this is something new that was added to the member definition screen. Prior to this, you had to spend quite a bit of time inputting information about all the plate sizes for your girder. And what we can do with this is we can greatly kind of speed up that process and make some initial guesses at the sizes of those plates for you based on proportions suggested and required within the AASHTO code. So things that we take a look at or we're going to take care of for you are things like the web thickness and depth, top and bottom flange thickness and width, and also a default material. And you can accept these sizes or you can revise them and then have us perform the optimization afterwards. So here are some of the guidelines that we use for this process. So for the depth of the web, we look at the maximum of the span length divided by x, and x depends on whether we're doing a curved or a straight, either simple or continuous span bridge. For thickness of the web, we take d over 150. For the width of the flanges, we take d over 6 for that. And then for the thickness of the flanges, typically it's the maximum of the width of the flange over 24, or that value has to be greater than 1.1 times the web thickness. So, and then we use the grade 50 as our default material for everything. So when you first open up the member definition dialog, you'll see some new icons across the top and some new tools. And the first one here is the Generate Plates tool. And again, we can do this for a specific member. We can do it for all the members in this group, or we can do it for all the girders on the bridge if you have multiple groups. And here's what it will look like once you've done that generate plate process. Again, whether you select web, top, or bottom flange, these will be fully populated for the full length of all the girders. And one thing that we do is we actually break these up a little bit. From the beginning of the first girder up to let's say the middle support. So in this case, I have a 2-span bridge. We actually break that up. We put the first 75% of it in here as one length, and then we have another 13% of it right here, and then the remaining 12% right here. And because those are typically where some of those breaks might occur in the long run, as far as you either needing to thicken up or make wider the top or bottom flanges. And then when it comes to the flange design optimization, we check a lot of articles in the AASHTO code because a lot of those are interrelated, and it makes it kind of an iterative a trial and error approach. And again, for the flange parameters, we're just looking at the width and thickness of these. And what we're coming up with or shooting for is to come up with a minimum area that passes the AASHTO code check. So we kind of combine width and thickness into a single component called area. And then from that, the structure has to be reanalyzed following any design optimization just to see if the changes that you've made have affected the structure in any way. So here's kind of what the dialog looks like when it comes to the design optimization part. We've got a tool up here called Design Optimization. When you select that, again, it's going to give you the same choices we saw with Generate Plans. It can either do it for the active member, all the members in the group, or the entire structure. And then once you've run that, then you would want to take a look at the design results. It'll also plot the results here in the elevation view. And there are parameters here for things like maximum thickness and the maximum width of any of these members that it will consider for the optimization process. But it is up to the user to go in there and change the values as far as the actual thickness and width of each of the plates. So again, the two parameters are combined into one area value. And then we start with kind of the input width and thickness as a minimum area, and we work up from there. And then we increase the area until one of two things happens. Either the flange code checking works or we max out on a maximum plate size. And then we'll take a look at those optimized design report for those changes. And like I said, you'll need to manually revise those and potentially rerun the analysis again. So here's what it looks like before you run the optimization. As you're running it, it'll pop up briefly a little status bar showing you the status of that optimization, and it's a very quick process. And in the end, it'll come back with the areas required here in the elevation view. So these darker areas here on the top and bottom reflect where we need more area for the top and bottom flange. And this is kind of what the results window will give you is something will look like this. And it'll show you, the input area for that particular, at that specific checkpoint, the required area, and then it suggests a potential width and thickness that would satisfy that that specific area. So let me transition over and open up the product here. So here's a bridge that I've modeled previously, and just to kind of show you, for those of you that maybe haven't seen Leap Bridge steel before, when we do the modeling of these structures, of course we're defining where the pier and abutments are located, and then from that we'll go back in and add a deck slab, and those slabs can be broken up in the actual porting sequences that you may want to do later on or consider during the analysis phase for various stages. And then you define the member groups, which is basically kind of your framing plan of where the girders are going to be located. And then you come down here and you define the actual girders themselves with this member definition tool. And then once you have the girders defined, then you can add things like we see here in this model, things like our cross frames and stiffeners and shear connectors. So today we're just going to kind of focus here on this member definition tool. So here's kind of what the girders look like right now, but I'm going to ask it to go in there and regenerate all the plates for all of my girders. So I'm just going to come here to generate plates, and I'm going to say go ahead and do that for all the members and all the groups. It says, are you sure? And I'll say yes. And very quickly it comes back with some proposed values for the starting height and thickness of the web, and it's done the same here for my top and bottom flange as well. And at this point, if I wanted to, I could go in here and change any of these values. For example, previously I had in here 14 inches for the starting width of the top flange, and I believe the bottom flange I had maybe 16 inches in there. And this is kind of what it's come back and initially proposed. But at this point, if I wanted to change those, I could. I'm just going to accept the values that it's generated here and say OK. And what the software is going to do is go through the process of updating the model based on those geometric changes to the plates. And then I'm going to just go straight down to the analysis tool down here and tell it that I want to do a line girder analysis. You'll notice we have both line girder and grillage here. I'm just going to do a line girder on one of the exterior and one of the interior girders. I'll go ahead and real quick run that analysis, and it'll just take about 30 seconds or so, and it'll run that for us, and then we can go back and take a look at that member definition window. Now another thing we'll do before I finish this whole process is we will also take a look at kind of a very early version or very early beta of the next version, and a few things that have been added to even streamline this process even further than we have already today. So we'll go back to member definition. And again, this is the version that I'm running here is one that you can download and install and use today. And so we'll go straight over here to design optimization, and I'll tell it that I want to do that just for the girder that I'm on right now, which is member 1. So I'm going to ask it to do that for my selected member. It's run the optimization, and then I'll go back into the design results here and say I want to take a look at those results. And again, what it's going to do is it's going to show us some values here in red where we don't have sufficient area of either top or bottom flange. In this case, this is my top flange. Here's my column for required area. And we can see that starting out here at about the 70-foot mark, we're just a little bit under design there, and then it continues on from there. So I'm going to go in and make some of these proposed changes that are listed here to the girder. So for that first part of the span there, we're missing just a little bit. So I'll minimize this out of the way for a moment. I'm going to go ahead and tell it for, let's say for this top flange, I'm going to go ahead and just kick that up and make that about 14 inches for that first length. And I'm going to do that for the ending portion of this as well. And that may cover part of our problem there. And then if we go back and look at that report that was generated, for the next portion there, it recommends 18-inch wide flange by 0.875 or something similar to that. Basically, we need about 16 inches here. So I'm going to try just going up to, let's say, a 1-inch thickness and a width of 16 inches, and I'll make that symmetrical here as well. And you can see how it's changing the area here on this particular diagram. The lighter color again is what we've provided, and the darker is saying what is required. And then lastly, right over the support itself, we can see it's calling for kind of an overall area of about 32.5 inches here. And I could go up to as large of a plate as it's calling for there, but maybe we'll try something different. So we'll say maybe 32.5 divided by maybe an 18-inch wide plate. So comes back with something a greater thickness of a little over 1.8. So I'm going to go back into here, and I'll say maybe we'll make that a 1.875 and 18 inches wide. And again, this is just for one of the girders, but you'll notice we've kind of satisfied the condition here. And what I can do when I'm done is I can come back up here to the top and say, go ahead and copy this to all the girders, and then we'll take a look at how it works for the rest of those. Now on to the bottom flange. So we've made the top flange portion here. We've satisfied the requirements so far. So I'm going to go in here and tell I want to work on the bottom flange. And first thing I'm going to do is I'm going to go ahead and thicken this up in this initial area here. So let's scroll down and take a look at the report. And we can see that it's calling for an area of up to about 16 square inches here in that first section. So I'm going to go ahead and tell it I want to do 1 inch thick and 16 inches wide for the first and last plate. So you can see we've satisfied that area now. And then that leaves the remaining portion here closer to the support. So again, real quick, I'll jump back to the report, and we can see in that second area there, again, we still need just a little over 16 inches there of area here for this bottom flange. So I'm going to try again, maybe just repeating that 1 by 16 that we have there, and see if that doesn't satisfy our need in that area. And then lastly here in the middle, it looked like it needed about the same 32.5 inch one that we had previously. So I'm going to go ahead and set that to the 1.875 by 18. like so. And again, now we've kind of fully satisfied this. I'm going to go ahead and tell it that I want to copy this to all the members. So now members 2, 3, and 4 all have the same area here. I'm going to go ahead and OK that. And then I'm going to go back and rerun the analysis just one more time, because that's going to affect the overall structure here. So again, I'll go back real quick, rerun the line girder analysis here for those two members. Again, give it just a moment to run. And again, you'll see, even though this is a lot quicker than what we previously had, it's even a little better in the November-December release, and you'll see in a moment some of the kind of neat things they've come up with to even streamline this a bit further. So we come back into here. Again, I'm going to go ahead and rerun that design optimization on the girder, and boy, it looks like we're probably really close, if not just fine, in all these areas. Let's check that same condition here for girder 2, and it looks like it's really close as well, maybe just a little bit here in the bottom flange in this second area right here. And again, we could real quick take a look at those results and see that we are pretty much spot on in each of these locations here. We're right at kind of the fringe there as far as the rounding goes. There's probably something that's just barely over 20.0 square inches, but otherwise we are in good shape at that point. So that's really all it takes to do, kind of work through very quickly kind of a flange optimization process here for your girders. Now, like I said, I do want to show, I'm going to go ahead and close this view, and I'm going to bring up another copy of the software. This is basically kind of the same bridge here, and I'll run through kind of that process here real quick. So if I bring up member definition here, the generate plates is the same. Nothing's really changed there. Well, actually, you know what? I take that back. On the generate plates tool, they have added some input here as well. So this is in the version that's coming out in December. Bill and his folks have added some options here where you can actually go in at the beginning and specify whatever values you want here. So for example, I could say I want this, I know I want a web depth of 42 inches, and I want my top flange to start out at 3/4 of an inch thick and 14 inches wide, and I want it to be no more than 2 inches thick at the most, and maybe no more than 28 inches wide or something like that for the size of a girder. But you can also specify your material properties here for each plate as well. So then I'll do something similar here, maybe on the bottom flange. I'll say I want this to be 1 inch by 16 wide at a minimum, and maybe no more than 3 inches thick and 36 inches wide. So when I click OK, it'll go ahead and generate those plates for me based on the values I specified. So actually, when I opened that window, what it was doing was showing me the exact same values we saw before, but gave me an easier way to go in and override those values. So I could go in and OK that, let it go through the process of regenerating this model, and then again, I still need to very quickly go in and do the analysis here. So I'm going to go ahead and pick, I'll just do one of the girders here, run it for that first girder, and then once I go back, you'll see how the report looks a little different, and some really neat little option they've given us for inputting the values. So when I go back in here, I'll just ask it again to do the optimization again, and again, runs very quickly. But now the design results actually show up in this window, and we can leave this open and kind of share the screen here with the member definition window. So it makes it a little easier to bounce back and forth between the two. And then I can actually see here, which plates were affected, and the proposed sizes that it's offering here that I need to change. So for example here, kind of mid-span, it's saying it still needs about 23 inches there, and I could do a jump all the way up to a 23-inch wide plate at 1 inch, or maybe use some other plate size there. So again, that's going to affect two different plates right there. So what I'm going to do is I'm going to come in here and I'm going to select those two plates. So I'll go to top flange, and that will be these middle two plates right here. And for, let's see, 23 inches, maybe we still leave it a 16-inch girder. Maybe we'll try like an 1.5 inch plate. So now that I've highlighted these two right here, what I can do is I can type in 1.5 and hit enter, and it sets both of those to 1.5 at the same time. And then I can come over here and select, for example, the width value here, and type in 16, and it sets both of those to 16 for me at the same time. So it makes this process a lot easier. You can select as many of these fields as you want, and then when you start typing and hit enter, it'll change the value in all those fields as opposed to having to maybe tab through and change each one individually. So a really nice little enhancement they've done. So again, same kind of thing for the bottom flange. We can see right in this middle area here, we need to make a little bit of a change here. It's calling for an area of about 24.75, and I don't remember what I did for that previously, but we'll try an 18 by 1.375. So again, I'll go in and select the two thickness values and set those, and do the same thing with that starting width value. So again, very easy, very quick process here to kind of run through. Go ahead and copy that to all the members, and then you could go ahead and rerun that overall analysis, and maybe come back and check the optimization again and see if it suggests any slightly different values. Okay, so that is member plate generation and top and bottom flange optimization. And again, real quick, I'm going to go ahead and mention the web design optimization part of this, and then we'll kind of open this up for questions. And so again, and Bill's even more excited about this part of the process, the web design optimization. But basically, you'll input, just like we seen in that window a moment ago, you'll input kind of minimum, maximum web thicknesses there, and you'll be able to specify whether you want to treat this as an unstiffened web, transversely stiffened, or transversely and longitudinally stiffened as an input parameter. And then from that, we'll report back to you web thickness that'll work for an unstiffened situation for the web, one that'll work for transversely stiffened using some maximum stiffener spacing, and then the stiffener spacing that'll work for the input web thickness that the user has specified. And we'll let you know whether or not longitudinal stiffeners are required, and if they are, the web thickness that'll work with those transverse and longitudinal stiffened using some maximum stiffener spacing, and then the stiffener spacing will work based on the input web thickness. So that's kind of where we're heading for in the December release, or at least one of the primary enhancements for Leap Bridge steel in the December version. At this time, like I said, I would like to kind of go ahead and open this up to questions and see if anybody has any questions at this time.
Hi, Steve. There's a question here. Does the optimization use one fixed size for the entire length of the beam?
No, actually it doesn't. The optimization reports that required flange size for each POI based on the smallest area that either meets the code requirements, or number two, reaches some limit specified by the user.
Okay, here's another question. Does this integrate back and forth with OBM?
OBM being our Open Bridge Modeler product. It does. Today, what you can do, let's say with the current version of OBM and Leap Bridge Steel, you could model this bridge in OpenBridge Modeler, and then once you have it modeled, it's literally a one-button click. You can say, I want to go perform all my analysis and design work in LeapBridge Steel, and it would push that bridge over to LeapBridge Steel for you. I'm told in the December release, we will actually start round tripping the data. And what I mean by that is if you make changes here in LeapBridge Steel to, let's say, the girder geometry, you make changes to these plate sizes in here, you're going to be able to have an option, a new option in here that allows you to update your OpenBridge Modeler model, that physical 3D model that you have, so that your analytical model and your physical 3D model stay synced up. So we're already doing that on the LeapBridge concrete side. Any geometric changes made to like the superstructure and substructure can be pushed back to OBM now. But like I said, in this fall release of both OBM and LeapBridge Steel, we'll be able to do that same sort of updating of any geometric changes that you make there, getting those synced back up with the OpenBridge Modeler model.
All right. And we have another question here. Can a check be done in allowable stress or load factor as well?
We don't have that today. Do you want to kind of address that, Bill? I
Yeah.
know this is primarily LRFD right now.
Right. This is just LRFD right now. So. Okay, another question. Does the optimization work for curved steel girders as well?
Yes, it does. We do pick up on those differences in force effects that are reflected in the code checking, and there was actually one of the equations there mentioned the value we use when we're computing those web depths depended on whether it was a straight or curved structure. So yes, we are accounting for those.
Okay, and question, can both the width and thickness be optimized simultaneously? I mean, I can go ahead and chime in on that one. We're starting with a list of available plate sizes, and based on the minimum and maximum dimensions that the user has specified, we come up with all the possible areas that of available plates that remain within the limits of AASHTO specifications. There, the maximum B over T at 24, and we set a lower bound too, so we don't have a ridiculously thick and narrow plate. But we compute all those areas. There's several thousand plates in that database, and then they get sorted by area, so we just increment that way. And sometimes when you have a structure where you have a fairly large lateral flange bending, sometimes a thinner, wider plate will work better than a narrower, thicker plate. But again, this is strictly looking based on area. Hope that answers the question. And there's another question here. Can live loads be adjusted to something other than HL93?
Yeah, you certainly have that option here in the loads window to select whatever vehicle you like. The default loads are HL93 for both Strength 1 and Service 2, but you do have a standard library up here of loads, and you can use any of those loads, or you can create your own custom loads and use those as well.
Okay. And another question. Will the optimized size plates always pass the code checking after you reanalyze it?
That's a good question. Not necessarily. Those moments and shears may change after that reanalysis and cause you have to go back and make changes to those plate size after the fact.
And another question here, can you check diaphragms for curved girders? And I'll go ahead and answer that one.
Yeah.
We do code checking on truss type cross frames. We do not do just like a plate diaphragm or something like that. And we do not do the end connections yet. We just do the member checks. Okay, does the optimization consider the erection stability, especially on curved girders? And the answer to that,
Bill. Yeah.
Yeah, okay. The only optimization considerations are whatever's in the ASTO specifications with the code checking. So if there are any concerns about secondary effects or nonlinear effects, something like that, no, that would not be considered. Just whatever's in the ASTO code checking. Okay, how is the deflection criteria checked if required by a state DOT? Well, actually, the deflection criteria is not enforced as a code check in lead bridge steel, but we do report the deflections, and that would be, it's considered an optional criteria, I believe, usually by a, like you mentioned there, a state DOT. So you would have to enforce that. But we do compute the deflections and give those values to you. Okay, another question. What parameters beyond the flange plates affect the optimized design?
Well, okay, Bill. Yeah, so I'll take that one. Things like girder spacings, your cross frame spacings, your web depth and thickness, span lengths, deck thickness, the actual material that's specified there, those all kind of play a role here into those optimized plate sizes that we come up with.
Okay. One more here about, someone's asking about hybrid girders, if those could be used in this optimization process.
Yeah, hybrid are taken into account because we do allow you to specify material properties here for the web, top and bottom flange. So you could certainly use different material types there, and those are considered in the code checking as a hybrid girder.
Okay, that's all the questions that I've see.
Okay, well, I want to thank everybody for taking your time out of your day to listen to this tech talk.